Chapter 9, Problem 75. Let's just read the question real quick. A tightly stretched horizontal high wire is 36 meters long. It sags vertically 2.1 meters when a 60 kilogram tightrope walker stands at its center. What is the tension in the wire? Is it possible to increase the tension in the wire so that there is no sag? Okay, so here's a picture of what's going on. And I've got some forces we can talk about in a little bit, but some important facts. The tightrope walker is 60 kilograms. The full length here is 36 meters. Let me get better in there. 36 meters for the rope, the high wire. And then the tightrope walker is sagging. You can imagine maybe they're carrying a beam or something. They are sagging the rope 2.1 meters down. So as the tightrope walker has a mass, its gravity is going to have an effect on them. So there's going to have the force of gravity, which is just equal to mg, right? And then there's also going to be a tension where the tightrope is held up, where the tightrope string is held up. So you can imagine a wall that it's held up to right here. And so there's going to be a tension pulling in the opposite direction, both to the left and the right. Kind of like some of it to balance and some of it just to hold the rope up. So the question is, what is the tension in the wire? Well, all we have to do here is to look at Newton's second law, which tells us that the sum of the forces is equal to the mass times the acceleration. And once we sum all of our forces up, we can do some calculations and find the tension. So here, just before we write anything down, let's talk about it real quick. There's one easy one we can start with. So we can look at the sum of the forces in the y direction first, because we want to look at the forces directionally and then combine them later. So if we take the y component of the tension forces, which is just going to both be up, right? Because there's one, if I broke down the vector, or both the vectors, I should say, one will have a negative x component, one will have a positive x component, and both of them have positive y components. So both of the positive y components will add up and make it so that there's essentially two, and also the same thing being here, that this similar angles, the law of similar angles tells us that theta here is equal to theta here, both of these places. So the angle at the bottom of this triangle is going to give us this. We can call it FTY, let's say. So the y component of the tension is going to have a sign attached to it, because we have, with this being, with the hypotenuse being the one that we know we want, which is the tension force, and the opposite of the angle leg of the triangle is going to be the force that we want to include as the y component, then we know we need to use sine of theta. So another way to put it would be sine theta is equal to opposite over hypotenuse, right? FTY over FT. So that we know FTY is equal to the tension force multiplied by sine theta. So we're going to need two of those for the y component. That's going to be positive if we sum the forces up. And then there's also going to be a negative one, which is pretty obvious. This is the gravity force, right? So that one will show up as well, but as a negative in the sum. And then for the x, well, we only have two forces in the x direction. One's positive and one's negative, so they're going to cancel each other out, luckily for us. So we really only need to worry about the y forces in this scenario. So as you can see here, it's very simple. Like I said, 2 times the tension force times sine theta minus mg is equal to 0. So you just need to do some algebra here. You add mg to one side, divide by 2 sine theta, and you get your answer. Now we may not know what theta is, but there's one way to calculate it. We can say that, 1 second here. Yeah, there it is. Yeah, so we can calculate it by saying tangent theta of, tangent theta is equal to, if we're going from the original, since we know the height and we know the half of the length of the rope, well, we know the height that the tightrope walker sagged the rope and we know the length from the middle where that they were standing to one of the edges, we can use those dimensions to calculate theta. If we use tangent, it's opposite over adjacent, so it's going to be 2.1 over 18. So if we do 2.1 meters over 18 meters, the units cancels out. We just have a number. Theta should be about 7 degrees. And in this case, where it's about 7 degrees, we can take a small angle approximation and just say that, well, sine theta is going to be about equal to tangent theta because the angle is so tiny. And in that case, we can just replace it. And since we know what tangent theta is, it's just 2.1 over 18, we can just plug that in as placement instead of actually having to use a degree anywhere. So what we get here is a Newton force at the end of the day, because our meters cancels out here, and we have kilogram meters per second squared, which is equal to a Newton. And if you multiply these numbers and divide, you should get 2,500 newtons, and that's the first answer. So that's the tension in the wire, 2,500 newtons. Then you also have to answer the question, is it possible to increase the tension in the wire so that there is no sag? And the answer is no, there's not enough. So here's more of that. Sine theta is about equal to tangent theta for small angles, and it's because the tangent inverse of that ratio is equal to about 7 degrees. But also, the answer to the second question, it is not possible to increase the tension so that there is no sag. This is because since there's always going to be a gravity force acting on the tightrope walker, the tension force is always going to be trying to balance that in some way because it's holding, it wants to be tight, right? It wants to hold up the tight walker. So there must always be a vertical component of tension to balance the gravity force. However, when you increase, if you look at the equation, we'll go back in a second. However, the greater the tension, so we have the greater than tension, right? It means the less the angle. So as you increase tension, the angle should get smaller, right? And so that means, I bet it could go vice versa. If we look at just this equation, let's say, then if we made theta bigger, well, if we made theta bigger, then it should get smaller. It should be dividing by a smaller number, which would mean that the tension would get larger each time. Or we can go to the tension as well. If we make it like this, let's see. If we have 2ft sine theta equals mg, we forget about the 2 as a constant. The mass is a constant as well, and this is a constant. Then the relationship is just ft is proportional to 1 over sine. And for small angles, we can also say that this is about equal to 1 over theta. So this is why that relationship works like this. When you divide by a smaller number, then ft is going to be getting bigger if you divide with the theta as a smaller number. But also you can switch the places and have theta is about equal to 1 over the force due to tension as well. And so you increase the tension, then the angle will get smaller. And that's it.